This is mini lesson 1.2 on average rate of change. So we're going to start by analyzing the graphs of two runners and thinking about average rate of change in the context of average speed. So below we have a table and a graph for runner A and runner B. And the first question asks us which runner has a faster average speed for the first 9 seconds of the race. So looking at my function, if I look at the first 9 seconds of the race, it's going to be on this interval of the graph between 0 seconds and 9 seconds. And on this interval, it's a little bit hard to see, but they pretty much have the same average speed or the same slope to the line. However, you can see runner A looks like they have a slightly steeper slope or a slightly more fast average speed for those in that first interval. So for the first question, I would say runner A has a faster average speed, and I could justify that by saying steeper slope on the interval 0 to 9. So from the x value of 0 to the x value of 9, that runner has a steeper slope. Which runner has a faster average speed from 9 to 20? So at this point in the video, I encourage you to actually pause and try the rest on your own, and then play and see if you agree with my answers. Which runner has a faster average speed from 9 to 20? So that's the second interval here from 9 to 20, and it's pretty clear on the second interval runner B is going to take the lead and have a steeper slope. At this point, I'm actually going to move away from looking at the graph and start noticing that I can draw the same conclusions from the table. So the second interval, 9 to 20, just focusing in on that interval for a second and comparing runner A and runner B on that interval 9 to 20. I can see that runner A got from 120 meters to 168 meters. These are distance in meters. And runner B got from 120 to 213 meters. So I'm going to pause for a second and think about how could I actually calculate the average speed for both of those runners on that interval, so I could just have another way to prove my answer. So what I could do is think about the equation for average rate of change. So what I am going to do for this equation for average rate of change, and actually you have a space at the bottom of your paper for this, is average rate of change is always going to represent some kind of change in y over change in x. We were practicing that last week with concavity. There's a few ways to think about that. We calculated it last week mainly using y2 minus y1 over x2 minus x1. Another equation that we used in the past is up on the word wall, and it is fb minus f of a all over b minus a. In the second equation, I'm going to go through lots of examples with this because it's been a while, but the second equation, what the a and the b mean is it's usually when we're given an interval on the interval a to b. So we we thought of A as our first x value, and then we thought of B as our second x value. So kind of three different equations, three different ways of thinking of average rate of change. The basic idea is always on the top of the equation we have some sort of change in our output value, change in y, and in the bottom of the equation we always have some sort of change in x, or change in our input value. Okay, so how would I calculate the average speed from 9 to 20? So what I'm going to do for that is I'm going to take for runner A, I'm going to take the change in distance, the change in y, which would be 168 minus 120, and I'm going to divide that by the change in x, the change in time, which is 20 minus 9, 168 minus 120. Let me grab a calculator. Is 48. And then 20 minus 9 is 11. I'm going to get my answer in decimal form, so I'm going to do 48 divided by 11, which gives me 4.36. I'm going to go ahead and repeat the same process for runner B. I'm going to take the total distance that they traveled, 213 minus 120, and divide it by the time it took them to travel that distance, 20 minus 9, and then 213 minus 120, 93 over 11, gives me 8.45. So it's clear from the math that I just did that runner B is faster. They have a faster average rate of change, or faster speed on that interval from 9 to 20, and I actually already knew that because I already said runner B was going to be faster from 9 to 20 seconds from the graph. So just quickly comparing the graph and the equation and making sure I can calculate that same information based on the table. All right, faster average speed from 20 to 30. It looks like it's going to be runner A again. 9 to 31. So that's all the way from 9 to 31. It looks like runner B is steeper on that whole interval. And which one runner wins the race? For that, I'm going to look at the two endpoints, and I can see runner A finished the whole race in about 38 seconds, and runner B finished the whole race in about 50 seconds. So if runner A finishes first, then they are the ones who win the race. So basic idea, at different points in the race, the different runners are going different speeds or going at different rates of change. And then ultimately at the end of the race, runner A is the one who wins. Okay, so how can I use this equation for average rate of change on a graph and with an equation? So we practiced this using a graph last week, so I'm going to go through this pretty quickly. This first point is 1, 3, and the second point is 2, 1, and to calculate the average rate of change, I'm going to do delta y over delta x. So I'm going to use y2 minus y1 over x2 minus x1. So here's my x1, y1, x2, y2. So I'm going to get 1 minus 3 all over 2 minus 1, which is going to give me a negative 2 over a positive 1, which gives me a final average rate of change of negative 2. So we actually did this exact problem last week. I want to pause for a second and think about why did I use this equation for average rate of change? Because I have two equations to choose from, right? I have my f of b minus f of a, and then I also have this this y2 minus y1 over x2 minus x1. So the reason I personally chose to use this equation is because I have two ordered pairs, meaning I have two x values and two y values. So two ordered pairs, which means two x values and two y values. So because I have two x values and two y values, it makes sense that I'm going to use this equation because, look, I have two x values and two y values to plug in. Contrast that with the next example we're going to do, example 2, where I'm asked to find the average rate of change between the interval x equals 0 to x equals 5, given the equation f of x equals x squared plus 1. So in this particular problem, I am given, I don't have two ordered pairs, like I don't have two x and y values. What I do have is two x values, and I also have an equation. So because I only have two x values, I know I'm going to be using this equation here. So the first step in this type of problem, what we normally did is copy down the equation for average rate of change, which is going to be f of b minus f of a all over b minus a. Then it's normally helpful to identify what is your a value and what is your b value. So I'm going to call this first x value my a and the second x value my b. Now I'm going to rewrite this equation, but every time I see a b, I'm going to replace it with 5, because that's what I just defined as my b. And every time I see an a, I'm going to replace it with this 0. So I have f of 5 minus f of 0, and then this b is going to be replaced with 5 minus 0. Okay, so now I have this thing that I want to evaluate, f of 5 minus f of 0. I don't know how to evaluate this. I can't just like subtract it. On the bottom, that's pretty easy. 5 minus 0 is just going to give me 5. But my question is, how am I actually going to evaluate like this expression, f of 5, and plug in a number? And how am I going to evaluate that expression, f of 0, and plug in a number? So one piece of information I have that I haven't used yet is this equation. So let's copy down this function, this equation that I was given, f of x equals x squared plus 1. So even though I don't have output values or y values, I have an equation, and I can plug my input values into this equation to find my output values, and then I can plug those into the top of the equation to give me my change in output over change in input. So what does that mean? Well, I have my equation, and if I'm trying to evaluate f of 5, I want to find what to plug in for f of 5. Guess what? I can evaluate f of 5. That just means I'm going to use my equation, and every time I see an x, I'm going to replace it with a 5. So I'm going to get 5 squared plus 1, and I'm going to ultimately get f of 5 equals 26. So now f of 5 is equivalent to 26. I can replace those two things with each other because they're the same. They have equivalent value. So this f of 5, I'm going to come back up here and I can say, okay, well, I know f of 5 is 26. For this function, when the input value is equal to 5, the output value is equal to 26. And then I'm going to repeat the same process, copy down the function again. And now I'm going to evaluate the second part, which is f of 0. I'm going to plug in a 0 for x, and I'm going to get f of 0 is equal to positive 1. So now I know this whole expression, f of 0, is equal to 1. And then now I have an expression that I can actually evaluate. So 25 divided by 5, which is going to give me a final answer of positive 5 for my average rate of change. Okay, we did a lot of these problems, and it was a long time ago. So now that you have this example copied down, you're going to move on to these partner practice problems. You're going to use the same two equations for average rate of change to solve these partner questions. There's an answer key posted on the home page, and definitely work with your partner to check your work and verify your solutions as you go. Raise your hand and ask questions. Good luck. Thank you for your attention.